General Physics Laboratory Mechanics. The table of contents of this preview is purpose, measurement and errors, one-dimension motion free fall, vectors, two-dimensional motion projectiles, Newton's law of motion, fractional and spring, conservation of energy, conservation of momentum, significant figures, making good graph. The laws of physics are based on experimental and observation facts. Laboratory work is therefore an important part of course in general physics. It helps students to increase their understanding of physics concepts and to develop skills in fundamental scientific measurements. It is useful to experience the difficulties of making quantitative measurement in the real world and to learn how to record and process experimental data. The first experiment is measurements and errors. The purpose of this experiment is to practice using several measuring instruments and identifying their error, recording results and doing calculation using the proper significant figures, representing results in table and graphs, and extracting useful information. Example, using the slope, identifying the source of errors and estimating the relative error in the result. From this instrument is the Werner caliper. This is a photo of Werner caliper. It contains a main fixed scale, a secondary sliding scale as shown in the figure, blue. The smallest division on the fixed scale is usually 1 millimeter. The sliding secondary scale used to indicate where the measurement lies when it is in between two of the marks on the main scale. For instance, if you move the sliding scale by a small amount, only one pair of marks will come into alignment. The reading on the sliding scale is found by counting the number of divisions to the alignment and multiplying by the precision of caliper. The precision of caliper can be found by dividing 1 millimeter by the number of the division on the sliding scale. The final reading is determined by adding reading on the sliding scale to reading on the main scale. A micrometer is used for measurements that requires greater precision than caliper. Though micrometers give superior precision, it can only measure very small lengths. It consists of calibrated screw that which, when rotates, helps in giving an accurate measurement. Experiment one-dimensional motion free fall. The purpose of this experiment is to study the motion of particles with constant acceleration in one dimension. You will study the relation between the displacement and time of free-falling object and check that it is consistent with the equation of motion. Experiment of vectors. The purpose of this experiment is to practice representing force vector graphically and mathematically, decomposing or resolving force vector into components, finding the resultant force vector adding vector graphically and mathematically. The experiment of two-dimensional motion projectiles. The purpose of this experiment is to study the motion of objects moving into two dimensions with the constant acceleration, for which projectile motion provides an excellent example. Students will practice how equations of motion are applied in this case, and how the different variables of motion are related. For example, students will predict the horizontal range of projectile shoot from various heights and angles, and will study the time of flight of projectile shoot horizontally and different muzzle velocity. Experimental Newton's laws of motion. In this experiment, Newton's first and third law will be studied. The purpose of this part is to determine how external force influence an object's motion by analyzing the velocity of number of objects. The purpose of the second part is to determine the relation between the force acting on interacting object. In this part, the force sensors are used to measure the paired force in a rubber band tug war and the paired force in collision of two cars. The experiment of frictional and spring force. The purpose of this experiment is to find the coefficient of static friction and the coefficient of kinetic friction for different surfaces, to find the spring constant for several springs. The experiment conservation of energy. The purpose of this experiment is to observe the potential and kinetic energies for the roller coaster and to investigate the conservation of mechanical energy for this system. Experiment of conservation of momentum. The purpose of this experiment is to investigate the conservation of momentum and kinetic energy of a system in collisions and explosions. Types of error in physics. There are two major types of error in the measurement of physical quantities: random error, systematic error. Random error is said to take place when repeated measurements of the quantity give different values under the same conditions. Systematic error occur when all the measurements of physical quantities are affected equally. These give the consistent difference in the reading. Percentage error given by this equation: experimental value minus theoretical value multiplied 100% divided by theoretical value. Significant figure. Measurements are performed with the instruments. No instrument can read to an infinite number of decimal places. Which of these balance has the greatest uncertainty in measurements? Accuracy and precision in measurements. Accuracy, how close a measurement is to accepted value. Precision, how close series of measurements are to one another or how far out a measurement is taken. When to use significant figures? To a mathematician, 21.70 or 21.700 is the same. But to a scientist, 21.70 centimeter and 21.700 centimeter is not the same. 21.700 centimeter to a scientist means the measurement is accurate to within 1 centimeter. How do I know how many significant figures? Rule: non-zero integers from 1 to 9 always counts as significant figures. For example, 3,456 has 4 significant. How many significant figures in these numbers? 7, 1, 40 had 1, 0.5, 1, 0.00003, 1, 7 multiplied by 10 raised to power 5 is 1, 7 million is 1. How do I know how many significant figures? There are 3 classes of zeros. 1, leading zeros are zeros that precede all the non-zero digits. These do not count as significant figures. 0.048 has two significant figures. How do I know how many significant figures? P, captive or sandwich zero are zero between non-zero digits. These always count as significant figures. 16.07 has four significance. Trailing zeros are zero at the right hand of the number. They are significant only if the number contains a decimal points. For example, 9.300 has four significant figures. 150 has two. 300 point contain three significant figures. Notice the decimal made the two zero significant. If the number was written as 300 without the decimal, then it would only have one significant. How many significant figures in this examples? 3, 4, 0, 1, 4, 2, 1, 0, 0, 2, 2, 1, 0, 0.0, 5, 5.00, 3, 0.004123, 8, 0, 0, 0, 050, 0, 0, 0 is 6. How many significant figures in this example? 1.2 is 2, 2100, 2, 5, 6.76, 4, 4.00, 3, 0.0792 is 3, 708300000 is 4. Exponential notation, rule of number written in exponential form. If your value is expressed in proper exponential notation, all of the figures in this pre-exponential value are significant. Example, 7.13 multiplied by 10 raised to the power minus 3 grams contain 4 significant figures. What about calculation with the significant figures? Rule, when adding or subtracting measurements numbers, the answer can have no more place after the decimal than the list of the measured numbers. Add, subtract examples. 2.45 centimeter plus 1.2 centimeter equals 3.56 centimeters. Round it off to 3.7 centimeter. 7.432 centimeter plus 2 centimeter equal 9.432 around centimeter. Multiplication and division. Rule, when multiplying or dividing the result can have no more significant figure than the least rival measurement. A couple of examples. 5, 6.78 centimeter multiplied by 2.45 centimeter equal 139.11 centimeter square. Round to 139 centimeter square. 5.8 centimeter multiplied by 9.6 centimeter equal, you can answer. Rules of rounding. In series of calculation, carry the extra digits through the final result, then round. If the digit P removed is less than 5, the preceding digit stays the same. For example, 2.34 round to 2.3. If the digit to P removed is equal or greater than 5, then the preceding digit is increased by 1. For example, 2.36 rounded to 2.4. Making a good graph. In this lesson, we will introduce you to the graph. Millimeter paper. Learn about the shape of the paper. It will look like this and can be obtained from libraries. Advantage of this paper, all measures and subdivisions are equal. The division in these points is the same on all points, and also in the vertical is equal as well as the same squares. These curves of the small squares that we did not see are equal in division, and this is what distinguishes the millimeters paper. How do we define the model of the equation, and how do you determine the slope of all of these, and are the following figures. And this is known to us: y, the function, x, the variable, and the t, m and t constant, and m is the slope. We will learn how to calculate it from the drawing in the next paragraphs. The free fall equation, y the distance the pole travels, and t is the time it takes the pole to travel the distance until it falls onto the sensor board. Using this equation, we calculate the acceleration due to gravity is g. We create this equation with the previous model by making it like this: y the distance, m is the slope, t squared is the x. We notice p is 0. This indicates that the line passes through the original points. We get to know this device for free fall experiment. When a pole falls, the device starts calculating the time of the fall until it reaches the last point. The distance is gradually changed, and the corresponding time is taken every time the pole falls. This is the table of reading. The greater the length, the greater the time, and the quarter of the time. How do we put the table on the drawing? We pick either of the two shapes out of the paper. We choose this format because it is suitable for this reading. We draw the axis and place the unit. We return to the equation. We notice that y is on the vertical axis and put the unit, as well as put the units and the value on the x-axis rt squared. We put the table in front of us, starting with the y-axis, and we notice the value are distributed from 0.7 to 0.75. We try to distribute these values on the y-axis, starting from 0. We notice the table that the largest possible value that we can take is 0.6, measuring that we can part this axis with the value 0.6. Here we put 0.20, 0.40, and 0.60 part first, the large particle, as we can see in the figure. And with this, we cover all the value with the y-axis. Now we start with the value of the horizontal axis, x-axis. We notice that these values are small and that there are some difficulties in recording them on the x-axis. So we write them in the following form. Notice that the values have become appropriate: 0.55, 0.73, 0.97, and 0.116. We multiplying them by 10 raised to power 3, 10 raised to power minus 3, and also multiplying the axis with the same value. We record the horizontal axis these values. Now the point on the x-axis are 20, 40, 60, 80, and 120. We notice all the values that we can put on the axis so that the axes are ready to put the result. We record the result on the axis and know the small significance value for 0 to dividing the large is 0.2 by 10. The small square is 0.02, meaning each small square represents 0.02. Now we put the result 0.727, 20, and 112. 27 and record it in the place and the remaining values 0.47, 0.57. We also record the values of the horizontal axis. We have from the first division, the largest division is 20 divided by 10. The square rises is 2. The first point is 55. The middle is 50. The second point is 0.73 here, and the same way for the rest of the reading. Now, all the points are ready on the two axes. We put the points and connect them with each other, and there are some irregular points. We draw the line this way and pass it through these points above and below. Then is an irregular point. We calculate the slope by law, which is the difference of coordinate y over the different coordinate of y and of the x coordinate difference. We call this physical is slope.